Hello, am I audible?
Yes, sir. Sir, we will start shortly, sir.
Okay, yeah, thank you.
Mukula, can you please start?
Yes, ma'am. Am I audible, ma'am?
Yes, yes.
Okay, ma'am. Thank you. A very good afternoon to one and all. I'm Mukula Zope from third year CSE department, and I welcome you all for this the wonderful session on the topic of microfluidic laboratory on the chips as cyber physical system design and security issues under the short-term training program organized by Computer Science and Information Technology, Artificial Intelligence and Data Science. I wholeheartedly welcome to Mrs. Sonal Patil ma'am, HOD of Computer Science, Information Technology, Artificial Intelligence and Data Science Department, then professors and learners, and special thanks to Dr. Sudeep Roy sir for accepting our invitation. Now, I would like to call Mrs. Sonal Patil ma'am, HOD of CSIT Department, to express her gratitude towards the session.
Thank you so much, Mukula. So, very good afternoon, everyone. And I again welcome you all to the very innovative and beautiful session of our today's STTP, that is on cybersecurity and blockchain technology. I wholeheartedly take this opportunity to welcome Dr. Sudeep Roy, sir. Sir, I, on behalf of GH Raisoni Institute of Business Management, welcome you to our STTP. Thank you so much for accepting our invitation. Though you are very busy in Japan, but still you took out time for us. That's a very blissful part for all of us. So thank you so much for accepting our invitation, sir. And once again, I welcome you. Over to you, Mukula.
Thank you.
Okay, ma'am. Thank you. Now, without further ado, I would like to give brief introduction of today's resource person, Dr. Sudeep Roy sir. He is a recipient of the Microsoft Research India. He received the MS and PhD degree in Computer Science and Engineering from the Indian Institute of Technology, Kharagpur. He has published 13 research articles in peer-reviewed journals, 24 research articles in international conference proceedings, holds 2 United States patents. Currently, he is a assistant professor of CSIT department in IIT Roorkee. So now, before hand over mic to the Dr. Sudeep Roy sir, I request all the participants to mute yourself for the smooth conductance of the program. Over to you, sir.
Oh, yeah. Okay, thank you. Thank you for your kind introduction about me. And yes, I'm going to share my screen. Just a moment. So, can you see my screen?
Yes, sir.
Yes, sir.
Okay. Okay, I think it is getting. Stop working now. I cannot see all the participants. Okay. It's good way. Get here. Okay. So, very good afternoon to all of you. And yes, maybe I'll take some about 1 hour and some time. So to talk about this microfluidic new technology, this is emerging technology, you can say. The microfluidic lab on a chip, laboratory on chip, which is a cyber physical system basically. So cyber physical, all you already know, because this is a kind of workshop or training program which talks about cyber security. So cyber physical means there is a computer part and there is a physical part in the system, and then you can basically design this kind of system with the help of computer. So basically the design also is a computation involved. So computer aided design is basically done. It's a subject which is called electronic design automation, because it's an electronic system and which is very small in size, and it will be basically the computer algorithms will be used to solve the optimization problems in the design automation, and then come up with the chip layout and then fabricate it, and then it is basically connected to some computer. So it will become a physical system after fabrication, and it will be connected to computer to control the system and also get the output of the system in the computer format, computer readable format. So basically, if I go with the title, then I will basically go with the first. Mostly, I'll discuss about its basically the technology and its design part, like what are the computer science topics which are basically involved in this kind of chip design technology, and I will talk about some aspects of security issue, because this is a hardware, and we all know by now that this cyber security is talking about the computer computing device or some computation involved in some hardware, and this is also required to be, those kind of hardware are also required to be secure, because there are a lot of challenges that several attacks may happen, and then you cannot get the correct result or correct data from that system. So okay, so now coming to that the title, that microfluidic lab on a chip, laboratory on a chip. I am telling lab on a chip is in short form. You can see the picture here in the title slide. Okay, let me take the pointer. Yeah. So here you can see that it is basically taken from a journal paper journal title. Means you can see the title page image or paper image. It is basically talking about some idea which is going to be explored, or it is being explored by the researchers, that is it possible that a biochemical laboratory or a pathological laboratory, like a room size shape, having several manpower working on that, to be made on a small chip. So basically, what are the tasks being done or they are involved in for diagnosis of our diseases and all these things. Then sample, blood sample and all these are taken, or human physiological fluids are taken basically to do some study and analysis and give the result. So this we all are familiar with this kind of laboratory, that is biochemical laboratory, and maybe we very common word is pathological laboratory. So we seldom go there for our test of blood samples. So whether this is possible to make this kind of laboratory into a small chip. So this is not very new topic, but it has been being explored by many years by many researchers, and also industries are there working on this kind of revolution in the biochemical laboratory, or the chemical, means you can say the point of care diagnostic kit development. So this you can say that interdisciplinary subject mostly, because it involves biochemical not reaction, maybe you can say that biochemical interaction, like biochemical fluids are taken into account. So it will require some knowledge of medical science, it will require some knowledge of biochemistry, and also chemical engineering sometimes, maybe also mechanical engineering, because many things are being mechanically controlled. And finally, means computer science is required, because this is a very tiny small chip, as we use in our mobile phone, basically in the computer or laptop, that processor. So it's a very small chip, so it cannot be designed by manual intervention. So it requires some computer-aided design tools. So how these computer-aided design tools can be developed, and which will be used maybe for developing a lot of such lab on a chip, and these chips should be very low cost, or it will not incur much cost, because it should be disposable. Because as we can see that in this current situation of pandemic, people are going for this RT-PCR test. So we all are knowing about this test, how it is being done. So there are a lot of kits people have developed also, the researchers have developed, people are using in some of the countries. And basically this kind of kits, if it is available, so we all know that it cannot be reused by many people. So it has to be disposed of. So the material science is involved here. So what kind of material should be used so that it can be disposable and also very low cost, at low cost, so that we can reach, means people can, the researcher can bring this kind of kits to the villages, poor villages, where this healthcare is a big problem. And this diagnosis is very important to save the society. So, so like this, you can see here that in traditional lab, basically we use manual intervention. So we use this beaker, and we use maybe multiple fluids, and use another pot we put into that, and we use test tube, pipettes, all these things, which are manually held devices. Now, on-chip laboratory, meaning there is a paper reference also in the Lab on a Chip journal in 2006 that tells that it basically, there will be some mechanism for automatically controlling the fluid flow through some capillary channel into a substrate, a small size device on a glass or plastic substrate, through which this fluid can basically they put into this into the channel, and then they can interact, and then finally the output can be diagnosed by the mechanism of some cyber physical setup. So this is basically the main idea, that how this main application area with which I want to go with in the following slides. So the outline is that for the today's talk is that I will first talk about the technology part, that what is lab on a chip, or LOC in short. We also call microfluidic biochip. So simple biochip word is also used sometimes. So all are basically interchangeably used to mean the same technology. And the first I will talk about the traditional biochips, and then I will talk about some advanced technology that has come up during last maybe decade by different researchers in different around the world, means by different researchers. And I will introduce those kind of technology, how they are, and they have been done experimentally, and they have published their papers, and also they demonstrated the system with some real life video that their chip is working. So I will show some of them to give you the flavor about this kind of physical system, you can say. And sometimes it is basically controlled by, most of the times it is basically controlled by cyber or the computer. So that is why it is cyber physical system. And then the third part, I will go to this design automation issues, which is maybe my research area. So I will talk about more in this, that how different algorithmic challenges are there for designing this kind of chip. And we will take the help of maybe the idea, the knowledge of computer architecture, operating system, and maybe compiler, programming languages, and algorithm design. So all these will come in some point of time, that how these subjects in computer science is also useful in design automation to solve the design automation problems for microfluidic biochips. And then at the latter end, I will talk about the security issues. It is basically a hardware system and a cyber physical system. So there may be different kind of attacks now possible. And some of them I will mention in this talk at the end, in that section. And then I'll conclude the talk. So first and foremost, that is what is the technology? So LOC, or lab on a chip. So we all are familiar with this biochemical laboratory and pathological laboratory, where there are several complex operations are being executed manually. So we need skilled technicians. So obviously, I cannot do this because I am not a skilled person in doing this manually, precisely control the fluid using the pipette. So this is a very high precision involved here, and that's why a very highly skilled person can do that. Anybody cannot do this. So this is why it is very, you can say that it depends on the skill technicians. And sometimes these kind of laboratories are also having bulky equipments, so which are looking very big and sometimes being controlled by robotic arms. And obviously, this kind of base equipments are incurring basically huge cost. So overall, the scenario is this, that the operations are very complex to handle very small amount of liquid or fluid, and skilled technicians are the dependent person, means we have to depend on them. And if there is any manual error, then we have to face that in the consequence for that. And there are bulky equipments which incurs a lot of cost. So the whole situation is like this, that it is basically time consuming, it is laborious, and it requires a considerable amount of fluid also, because we cannot precisely control very small amount of like some nanoliter volume by manual intervention. Whereas if we have some kind of computer aided or computer controlled system or automated system, then we can control the amount of fluid at the picoliter volume also, or maybe at the femtoliter volume also. So that is the main challenge, because these fluids are very costly, because some of the fluids, some of the reagents which are used in the biochemical laboratories are very costly, which are being purchased from abroad in different countries, who are the developed countries. And by buying those fluids, we are basically investing a lot of monies in that to at least get the test done, to check that whether we are infected by the disease or not. So this is why that healthcare and this healthcare cost need to be reduced. So this LOC has a very huge market in worldwide in different developing countries. So people started working on this, that we should not rely on go for this manual intervention based system. Let us try to make it automate and make some small chips. And at the end of the talk, I will show you that what kind of development already being done by controlling some chip using mobile phone. Okay, so I will talk about that at the end. So finally, this LOC will look like this. It will be handheld device. It is a photograph taken from a real chip from a journal which was published by some researcher, and then it is basically the real chip. You can see the colors are basically integrating different fluid, and these gray or you can say the brown color how is it basically working. So I told you earlier, UC Berkeley with his lab, in their website it is there, and they basically, so not only there are many universities, many research groups from industry and academia, both are working on this. So this is a well-established subject now. So this is lab on a chip of microfluidics. Is basically, it involves physics, chemistry, biochemistry, nanotechnology, and computer science. So it involves a small volume of fluids, even it is at the level of femtoliter, although I have mentioned here microliter, nanoliter, and picoliter. Sometimes it's basically also, nowadays people have developed chips with femtoliter volume also. And this is very small chip, and it is being controlled by battery, being a very small chip for controlling the microcontroller, which is controlling this the physical chip. So it basically consumes low energy. Okay, so main purpose is that it should be very easily accessible, easily available, and low cost also. So I'm showing one video here. If it is running, I don't know. I have to go to the pointer mode. Oh. Yes, I think here. So this, okay, I'm reducing the volume, so I'm muting. So it is showing that some manual intervention involves a lot of tasks and it is laborious for the technician to handle all these fluids in the laboratory, biochemical laboratory. And if these automated machines are being used, and sometimes after this, during this process, if she has made any mistake, then she has to repeat the whole process again. So she is very much worried now that what I have done, I did some mistake. So then this new technology is coming up, and basically it is available by this company. The company name is Illumina, and they have developed this system. It's called NeoPrep system. It is basically for testing purpose for some biochemical fluids, and you can see that how these fluids are moving, and this is being controlled by computer program, and you can see the blue color fluid. This is basically moving on the chip, and now the whole task, a lot of tasks parallelly can be done, and it will be easier for the technician to control to get the results very fast. So if we go with this microfluidic biochip, broadly these are categorized into two. So there are two types of microfluidic biochips in general, broadly classified. One is digital microfluidic biochip, and another one is continuous flow microfluidic biochip. So this is similar to the electronics that we have studied. So there are digital electronics and analog electronics. So just keeping analogy with that, electronics, this fluidics is also like that. So digital means here that you can discretize the fluid. That means you can create small droplet. The small drops are called droplets, smaller than small droplet, that is droplets. So these droplets droplets can be created, and you can use this droplet to conduct your biochemical test. Whereas in continuous flow microfluidic biochip, these fluids are basically flowing through the micro channels, and these channels are etched on the substrate. So there is a substrate which is maybe made of this glass, or it may be sometimes PDMS. PDMS is basically a plastic kind of material, polymer kind of thing. So this kind of material, this is being done. And in case of digital microfluidic, the phenomena is the physics behind this is EWOD, which is electrowetting on dielectric. So I will discuss this in the next few slides, that how it is basically working, and then we can understand that why programming is required for this. And similarly, for the continuous flow microfluidics, there are micro pumps, so small pumps on the chip to push the fluid through the channel, and there are valves to decide the direction of the fluid. So if there are junction, then there may be multiple valves, and they will decide basically that in which direction the fluid should go. So depending on the desired application, the programming is important to control these micro valves and micro pumps, and these are essentially being done with the help of microcontroller. So whatever algorithm or programming we will be discussing are basically for the microcontroller, which are controlling this kind of devices, this kind of physical system. Okay, so in case of continuous flow microfluidics, this is a video taken from a research done in MIT, and it was published in Natural Computing Journal in Springer. It's last decade. So you can see here that the fluid are basically moving through the channels, and there are valves which are basically controlling their direction of movement, and then multiple fluids can be loaded into a mixer. So this circular shape is called a mixer. So you can basically mix two different type of fluids, or three different type of fluids, or multiple different type of fluids in a particular circular mixer. If you can control the valves accurately, or means as per requirement, then you can achieve this mixing. So in continuous flow microfluidics, basically this circular mixer is the main processor, you can say, in a chip. in VLSI we have studied, means in computer science or maybe computer engineering. So in mobile or in laptop, we have processor, we have memory. So in this kind of chips also, we can think of these chips that we have processor and we also have memory. Memory means the storage unit. So there are also some channels which are used for storage unit. So this is one kind of microfluidic biochip. So this diagram is showing that how these valves are being controlled, basically. So this is much more detail about its device, the physical part. So maybe it's not very interesting to discuss in this workshop, but still I am going to explain the simple example that if you are giving water in your garden with a pipe, you have a long pipe, and you have put your leg on that, your feet on the pipe. So it can be thought of as a valve, right? So you can switch off the fluid and the water flow to the garden on the other end. When your tap is open, you can put off your leg, and then you can see that the water is going. So the same thing is being realized on the small chip by using two different layers of fluid flow. So one is control layer and another one is flow layer. So you can see the blue color layer is basically flow layer through which the fluid, actual fluid, is being flown, and you have another, this red or orange color layer means in which there is another channel, and through which you can send the other fluid to create the pressure on the bottom layer. So like this, you can switch on or off or the valve. So this is basically creation of a valve in the continuous flow microfluidics. So this is being very, very micro scale. Just the view, this cross-sectional view is showing that how it is basically working. So not going into that much detail, just I am trying to model that system. So here you can see that there are junctions. Maybe it is there is no junction like S, the first one. So only one valve you can put in the channel, and you can decide whether you want to flow the fluid in the right side or you do not want to. So like this, you can think that, so this is a valve, and similarly if it is a T junction, then there will be 3 valves requirement, and if there is a you can say the plus sign type valve or X cross type valve, then you will be requiring 4 valves. Similarly, as we have seen in the video, so we have a circular mixer, which is the main processor, and there are several different fluids are being loaded into this processor or the mixer. So you can imagine that there are requirement of multiple valves, and you can also think that these 3 valves here, you can see V4, V5, and V6, they are basically constituting a micro pump, because when these valves are sequentially switch on, or maybe you can say that closed, then there is a motion within the fluid in that circular chamber is that motion is created, and this again switch on and switch off again sequentially, it creates a circular motion within the mixer. So this is how basically, without manual intervention, just by controlling the valves, you can mix multiple fluids in the this ring-like mixer or the circular mixer. I will discuss about this application graph and biochip architecture in more detail in the next few slides when it will come. Before going to that, I want to also give you some details about how these digital microfluidic biochips look like. So this video is taken from Wheeler Laboratory, basically Professor Wheeler, his microfluidic laboratory from University of Toronto in Canada. So what they have done, you can see this, not they, which there are many people have done, but this is the video from them. So you can see that there are multiple electrodes. These white squares are basically, so there are some big squares and there are small squares. So these big squares are basically the reservoirs of the fluids. So there are 5 different fluids already loaded of different fluid color, and you have to basically create the fluid droplet. small droplet from these larger electrode reservoirs and move them to the smaller electrode region and make the fluid mixed with each other. So you can see the video and then feel that how different colored fluids are being handled, or maybe the droplets are created, and then they can be mixed by using the electrical voltage basically here. So how these electrical voltage are being applied, it is basically, you can see for each and every electrode, they are being controlled by these wires. So these are all metal electrode. I will discuss the cross-sectional view of this chip also, so that you can understand how this is working. Then these wires are basically controlled. So using these voltages to these electrodes, actually this dragging force to the fluid is being applied, and then the fluid starts moving. And this phenomena is called EWOD, that I told earlier, that electrowetting on dielectric. So let's go to the next slide, and here we have this cross-sectional view of the chip. So you can see here that on the substrate, which is basically essentially sometimes glass or sometimes PDMS, on this gray, okay, maybe I should take the pointer. So on this, these are the electrodes you can see here. So these are of some material which is called ITO electrodes. ITO means indium tin oxide, which is a transparent but metal kind of conducting behavior. So this is the material that is used, and on top floor, on the top plate, this is bottom plate, this is top plate, and the droplet is sandwiched between these two. So somehow this is adjusted, this is not hanging. It is basically having cantilever and all these things in the mechanical structure, so that the droplet can move in between these two plates. But these two plates are is materially differently. There is some physics involved that how this droplet can move. So we have this glass plate, and on top on these you have this metal electrode or the ITO electrodes, and on top of this you have pyroline, and this pyroline is a material that is dielectric medium. So it basically do not give the contact. It does not create the contact with the droplet from the electrode, because if the fluid is in contact with the electrode, then it will be electrochemical reaction that will happen, or it will basically ionization will happen. So that is not desired here. So basically we do not want to make any electrochemical reaction. So we want to see the biochemical reaction or biochemical interaction. So that's the purpose of this biochip. So that's why this is the dielectric medium which is kept, and on top of this there is a Teflon AF coating. So Teflon is a material that is used in this non-stick frying pan, so which is used as a hydrophobic. So if you have the water droplet on that, it will create a spherical shape, almost nearly spherical shape, as we can see in the lotus leaf. Okay, so this helps the fluid droplet to not to wet the surface, but to stay as a spherical shape. And if some force is applied on this droplet, then it can be easily moved from that position to another position. And there is a physics behind this that is a very well established equation, physical phenomena, that is called EWOD, and the equation is known as Young-Lippmann, two scientists named by two scientists named Young and Lippmann in 1948, and it says the simple thing that if you have applied the voltage V to the adjacent electrode and you have a contact angle of the fluid θ0, then the new contact angle will be this one. How you can calculate the new contact angle, and if you calculate this, then you will find means how this force is being applied. So this voltage application actually creates the dragging force, and it's basically changes the surface tension, or you can say the contact angle. So this is actually the mechanism. So maybe this is not very important, but these questions may come. So that's why I just wanted to discuss why programmability will be required. We can understand after understanding the basics of this kind of chip. So now if we have a chip layout like this, some two-dimensional array of electrodes, You can see in the first figure that the top view. So now you have to control these each and every electrode at the particular time, so that the fluid droplet can move from one electrode to another electrode. So depending on the desired application that you want to implement on the chip, you have to write the program to control these control pins. So control pins are basically connected to these electrodes. So there is a microcontroller which is having its own memory. You can say ROM, and in this ROM you can put the program, or you can have a RAM also. You can download the program and then load into this, and then this will control these control pins or the electrodes. So this is essentially being done in this kind of cyber physical system. So now maybe some of the basic operations is important to know, because I will talk about the design automation problems and also what are the different tasks being done on the microfluidic biochip, especially this droplet-based microfluidic biochip. I am talking about digital microfluidics here because it is more programmable because we have a regular array of gridded array of electrodes. Okay, so let's start the video and then talk. So I can reduce the volume. So here you can see a video has been taken from the same Huidal lab, and they are showing that how these droplets are being created. So what are the different basic operations? So the basic operations are dispense. So droplet creation itself is called dispensing, and then mixing, and transportation is involved because you have to move from one location to another. And you see this interesting part, that is split. So you can also split 2 unit volume into two different 1 unit volume. Okay, so this is what has been explained here, and these are actually real chip they have done. Okay, so there are real chip videos also. So I think these are the main basic operations, that dispense, transport means move, merging means you just merge 2 droplets but do not mix them, and mixing involves that you merge and then steer them. That whole merged volume you just rotate within a confined area. And then splitting is as simple as that you have a bigger volume and you can make it half. Okay, so if you apply equal and opposite force in two opposite direction, then you will find that you have splitted the droplet. You have splitted the larger volume into small volume. Essentially, it is it means not essentially, means maybe ideally we can think that this is equal volume, both the volume. Maybe this is the ideal case. We are assuming that this is balanced splitting, but in real scenario there are errors, so it is not like that. So in real practical life, when splitting is happening, then there are unbalanced splitting. So some is having delta error, means delta positive and delta negative. So there are some automation problems which involves this error also. So we need to talk about that. We need to address those problems, how to automatically correct this kind of error or something like that. Okay, so there are other operations also which I have put here in black color. Means after splitting, those are basically derived operation. So derived means that maybe these basic operations, combining one or two of them, you have derived this operation, like detection. So what is detection? You have to move the fluid droplet from the current location to another location where actually the detection unit is there. So basically, I will talk about detection units in the next slide. So basically, not all the electrodes are having the detection unit, because detection unit is costly. Detection means it can detect the concentration, or it can detect the volume of the droplet. So if it can do so, there is some physics involved, and we need to devise some. We need to attach some device externally, which is called sometimes second sensing device, you can say. We need to apply sensors. So sensors are costly, so that's why the many such sensors are not included. So we need to move that droplet and put into that detection unit. So that's basically a derived operation. And dilution is similar when you are basically taking a fluid and you take water, or water-like fluid, like you can call this fluid as a buffer. So in biochemical laboratory, basically NaCl, KCl, these are the solutions which are taken for as a buffer, and then they are mixed to dilute the basically concentration of the sample, the main fluid. So this is a very important task in all the biochemical, almost all the biochemical laboratory protocols. So the biochemical engineer, they or the lab staff always do this to identify the strength of the sample, or you can say that if it is yes, you all know that in case of drug discovery also means we need to decide the dose. So we need to dilute and then see the reaction. We need to dilute and see the reaction. So then we decide that people decide that this is the particular dose which will be effective. So this is the important test, derived operation. So like this, there are other operations. I am not going into detail of those, the perfusion, heating, and cooling, and metering, all these things. So I was talking about the sensing module and detection. And at that time, I told that there are two parameters which are involved, which are very important to know of a droplet. One is the concentration of that fluid in that droplet, and the other one is the volume. Okay, so the first one is basically measuring the concentration. So how it is doing? So it has a LED at the bottom, below the bottom plate, and this emits the light. And this is the detection unit, this electrode. So the light is passing through the electrode, and this is transparent electrode because it is made of ITO material, and these all materials are transparent, so light can pass through these layers and then pass through the droplet also. And then it also passes through the top plate and goes to the photodiode. So you can see that there is a photodiode. So this is as simple as that photochemistry, basically for photoelectricity, for which Einstein got the Nobel Prize. So basically this is the arrangement, that LED and photodiode arrangement, which is basically helping this chip designer to calculate the concentration, or basically from the calibration of some already taken data, the unknown concentration can be determined. So this is one sensing module or detection unit. The other one is the capacitive sensing circuit. So how it is being designed, or how it is being acting. So here basically we are going to measure the volume of the fluid. So we can imagine that the droplet is in between two electrodes, and these droplet is basically non-conducting material. So it is behaving as a dielectric medium, and two electrodes are basically metal electrodes. So it is forming a parallel plate capacitance. So that's why it is called capacitive. So if your volume of the fluid is less than the desired one, you will have less concentration, less capacitance value, or more capacitance value, depending on the area. So we all know that parallel plate capacitance is basically calculated by C equal to epsilon A by D. So epsilon is the permittivity, so that material, that fluid, that permittivity will be there, taken, and A by D. So A is the overlapping area between two electrodes. So this overlapping area changes when the volume of the fluid changes. So this A changes, and D is constant because two electrodes are equally distant always. So this is not changing. So from this capacitance change, which is basically converted into voltage change in the periodic square wave by this Smith trigger arrangement, it basically gives the measurement of the volume. Okay, so this is by how the sensing unit or the detection unit are created, the basics behind that, the details behind that. So now I will show you some applications that how this kind of chip has been used already. So in the commercial products, So this is one commercial product, and it is known as Babies. And the lead support engineer is demonstrating the device, and it is containing a microfluidic biochip inside this, and it is connected to the computer, and you can load the sample for which sample is basically taken from the newborn baby. So for the newborn baby, we cannot drag too much blood from the baby. So we have to take very small amount of blood, and we have to do all the screening, all the tests, means depending on the situation. So they have developed this device for doing that purpose, and they are putting they are showing that this is the microfluidic chip you can see here. So it's very small electrodes, and they are loading the fluid into this chip, and they can conduct all the screening at a time with that small amount of fluid. So this is one commercially available things which are available in US and Europe maybe. And this Genmark is another company who actually prepared a E-Plex, that is the device name, for molecular diagnostics. So molecular diagnostics is very important for maybe the very handy example is coronavirus. So molecular diagnostics have been done. That's why people are able to know that this is a new variant, this is another variant, so like this. So they basically, this is a biochemical laboratory which are being performed. So they have developed a E-Plex system named to do this molecular diagnostics for the sample, which is containing the maybe some organs or organisms or something like that. So they basically do these using these microfluidic devices, which you can see here. They have some cartridge kind of thing. They insert this, and they can see the inside this what is happening. The fluid is basically moving from one location to another, and they are basically going to this digital microfluidic biochip you can see here, and they are creating droplets, and they are doing the mixing and all these things automatically, and then detection is being done at the end, and then results are basically shown on the screen, in the computer screen or display. So this is how they have basically they are doing PCR formulation. Here you can see PCR, all we know now, RT-PCR test. So PCR, polymerase chain reaction. So they're doing that automatically and quickly getting the results from there. So this is how these kind of devices are, these kind of systems are already marketed by different. So they're studying the molecular details and all these things for a particular sample. So this kind of devices, these are the basically available chips by the industry. So I think till now I have discussed about two basic type of microfluidic biochip. So one is digital microfluidic biochip, another one is continuous flow microfluidic biochip. Now I will talk about some advanced kind of microfluidic biochip, which are maybe some advanced versions of those two types. So one is this MEDA, that is called, the full form is basically micro electrode dot array, a digital microfluidic biochip. And the second one is PMD, that is programmable microfluidic device based microfluidic architecture. So these both were developed around 2012 or 2011, last decade. And this last one is the paper-based digital microfluidic biochip. So the digital microfluidic biochip we have already seen, but this is paper-based. So the substrate is not the glass or not the plastic. It is on the paper, just simple paper. They have just printed on the paper the layout of the chip, and then they perform this. So it made very low cost. So this is a new kind of technology. You can see the electrodes are different shape. So let us go with one by one. So MEDA is one kind of chip. I will just run the video and showing just important part of this video to you. So maybe it's very small, but it's okay. Maybe there are basically multiple electrodes combined together and giving them means a fluid can take a can seat on multiple electrodes. So it can take a different shape. So you can see here that they can change their shape. So if they can change their shape, you have, and they can move in different direction. Like in the previous DMF, digital microfluidic biochip, they were only able to move in the horizontal direction or vertical direction because it was 2D rate. Now you have made more granularity into the electrode array. So in this MEDA, so you have now flexibility to move the droplet, or the, you can say, the fluid, bigger size fluid, in any direction. So it actually reduced a lot of cost, and this is the latest advanced technology, you can say, till now. So they can move the fluid droplet in any direction. So one video is there, so it will show that, yeah, this one. So the droplet is moving in diagonal direction or horizontal or vertical direction. So this is the main specialty of this kind of new digital microfluidic biochip. And there is another kind of continuous flow microfluidic biochip, which is programmable. So you can see the fluids are moving through the channels, but these channels are made in a fashion where there is a regular grid-like structure. So you can see there are multiple valves like these, and these are the cells which are already filled now. These are the cells in which the fluid can be loaded, and each and every valve, every cell has their 4 neighbor valves to decide that in which direction the fluid can be moved, depending on the valve are closed or open. So like this grid-like structure is a new invention. This is from Switzerland, and they published this work along with their experimental setup, the video of that in Lab on a Chip journal in 2011. So these are the most advanced technologies, and the last one is, last one is this one. This is just the new technology which was done in South Korea, and this is the Professor Sin. They basically used a carbon nanotube material. So their research is mainly on materials of this kind of chip. So they focused on low-cost microfluidic chip and printable microfluidic biochip. So they have printed using this carbon nanotube material on the paper, and those are low cost now. So they have commercialized also. They have their own company to sell their biochips. So their chips can be printed on a printed paper. You can see they're on a newspaper also, and then they can do the test. So they are trying to market this kind of chip for the developing countries for low cost diagnostics. Okay, so this, I think already I have discussed one by one in that slide. So maybe now I will go to the discussion on the design automation problems. That's main. Where is the computer science? I think by now you have understood that how these chips are working, and where is the similarity with, where is the need of computer science? Like, where is the need of programming? Where is the need of? So I'll talk about those slightly now. So given a biochemical application, you need to map on the chip layout. So that is main task. So you have 2 tasks basically. One is that means you have to design the chip layout, and the second one is that you have to control the fluid, you have to control the electrodes. I'm talking about digital only here for this simplicity of the discussion. So now the second task is that you have to control these electrodes in such a way that you can perform the desired mixing and splitting operations of different fluid droplets, specifically saying. So what is input there? So input is basically a protocol. It is known as protocol. It is just as simple as sequence of instructions, which basically the biochemical laboratory experts use as the bioprotocol. So they need to perform some biochemical laboratory reaction on their benchtop setup using pipettes and all these test tubes. So they know that after taking these two fluids, I have to mix them at this ratio and then keep this for some time, maybe 15 minutes, and then I have to heat it up, and then I have to put the third fluid, and then see, I have to cool down it, and then something to do in the next. And after some finite number of steps, they actually detect that, or analyze the resultant. So this is how the general template for any biochemical laboratory. So they basically follow some kind of instruction, sequence of instructions. Those are called sometimes bioassay, or sometimes called bioprotocol. So we'll refer to those as the bioassay or bioprotocol. Those are basically real life bioprotocol. Real life means that in reality, in the biochemical laboratory, these are being used. So this, in the left figure, it is showing one such example of bioprotocol. And if we carefully look into this, and the right side is showing the layout, that's okay. If we look into the left side figure, we can imagine that this is a graph. This is a directed acyclic graph. Okay, so the nodes are basically talking about the operations, and the edges, directed edges, are basically the sequence, maintaining the sequence. Okay, so now here, coming to this point, I have another thing to share with you, that there was a need that how to standardize this kind of protocols, that previous one I have shared here, into some format which can be read by the computer. So computer readable program, or the instruction, which can be used as the input for the designer who will design this kind of layout. So given this instruction, sequence of instructions, or the protocol, there is a need of programming language basically here. So one such development was done in Microsoft India only, in Bangalore. So they had this project last decade. So this is talking about basically the C++ kind of language they developed, that is called biocoder. And they have explored that, they have shown that this is, they have demonstrated basically with their hardware setup also, that this program is used for automatically controlling the hardware system. Okay, so depending on the protocol. So here you can see that the syntax is similar to C++ language. So in hash include some header file. So where all these functions are written, and some hash defined 60 something, some variable has been defined, and then void main, and then start protocol, the name of the protocol. So it is some different kind of PCR test. So there are many different kind of PCR test. We are doing RT-PCR for COVID, but this is long. It has long history and long, large number of variants of this test. So here we are talking about this particular bioassay or bioprotocol, and it is taking new fluid. So new fluid is looking like a constructor, like in C++. So it's creating an object. Like in physically, how it is interpreted. So it is interpreted as that NaOH is the fluid, and this much amount of NaOH fluid is taken into the test tube. You can say like that. So they have developed this for their continuous flow, or the robotic arm based system, which basically deals with this test tube only, and just the pipettes are controlled by this program. So the robotic arm will take this program and then control this. So this program is biocoder language. The program is looking like a C++ language, and this is how they developed and they have shown on their application also. In simple language, if we think that, as I told you, that the bioassay or bioprotocol is looking like a graph, the directed acyclic graph, so DAG. So how we can write this graph? We can write in a text file like some set of nodes and then some set of edges, and these edges are directed. So if we follow this slide, then there are nodes. So node has node ID, node type, which fluid to be considered or dispensed. So this is a dispense one. So dispense 1 operation, dispense 2 operation, dispense 3 operation. So each operation are identified is node are identified. So you can maintain attributes for each and every node, set of attributes, and you can have the edges. So edges are basically directed edges. You can also maintain the attributes for edges also, that one edge indicating sometimes maybe wait for 5 minutes, so that maybe you can add. So this different discussion. Maybe you have set of nodes and you have set of edges. That's the main point here. So if you can write down a sequence of instruction, you can always write down like this. Basically, a sequence of instruction can be written as a directed acyclic graph, and you can write down as a file here as it is shown. Then after reading that file, you can see that, visualize also that what is your directed acyclic graph. And this is actually validating that what you wanted to do is written in a file, and now visualizing that file and see that it is basically that directed acyclic graph, which is essentially basically giving the idea of that bio protocol. Okay, so now let us talk about one discussion about this synthesis or this kind of chip design. So how this is being automated, is automatically designed by computer by solving some algorithms. So here we are taking one example that is called multiplexed in vitro diagnostics. And this is basically taking 4 different samples. You can see here, plasma, serum, urine, and saliva. And for each of these diagnoses, like glucose measurement or lactate measurement or pyruvate measurement or glutamate measurement, in each of these, you know that which reagent has to be used. So now, if you want to do all these diagnoses together at a time, so you have to take all the samples and mix with all the reagents and then detect at the end. So that has been shown in this directed acyclic graph. So this graph can be thought of as a single graph if you have no operation kind of dummy node at the end, and you can have a dummy node the start operation. So by this, you can think that this is a sequencing graph, and you have to do all these operations to get the measurement. So here only they have shown in this figure, only 2 samples have been taken and 3 different reagents have been taken to do 3 different assay, enzymatic assay to run. So for that, this is the graph. So this is also called directed acyclic graph, or you can say sequencing graph model. So this is how the problem is modeled, how your input is modeled for doing the for solving the problem in computer. Okay, so after going to the computer, so you have to take the input and then you have to run your algorithm. So now you understood that this is the graph. Next is that once this graph is given, which is sequential graph or directed acyclic graph, and you also have some kind of library. So this is called module library. So each and every module is made of some dimension, like right, like in 2D array of electrodes, how many cells or how many electrodes you have taken. So if you are considering this module 4x4 module and your hardware is 2x2 electrode array, maybe this module may take 10 seconds for mixing of particular set of fluids. So you know that for this pair of fluids, you have maybe 4 different mixing module options. So mixing module. So there are 4 different options. Now you have to choose which one is the best. Obviously, you will go for the faster one if you are choosing to optimize your design for time. But if you want to optimize your design for space, then you will choose the smaller area module, right? So like this, there are different optimization criteria to solve this problem. And this is called, and here also involved another thing, that is, given this input graph, you have to schedule that. Schedule means in terms of timestamp. So timestamp is the minimum time that is considered as a, you can say that for one operation to complete. And then depending on the time taken by the mixer when it is being assigned, means to some mixer module, you can decide that what will be the start time, what will be the end time. So like this, your graph should be scheduled also. Like each and every operation may take different time to complete their operation. So that's why the schedule graph will look like this, which will tell that 0 is the timestamp where it starts, and then depending on the dependency, this directed edges, their graph is scheduled. And at the end, the last operation is finished at 19th timestamp. That means that this is the time of completion. So this is scheduling problem. And that is another one is that module binding problem. So these two are the algorithmic problem which are well studied in literature, and you can search for this and then get the details. So given the bioprotocol, the first task is to do the architectural level synthesis, and which involves these two tasks. So one is scheduling, another is module binding. The second one is this geometry level synthesis, which is basically physical design automation. So that means that you have to place this module on the chip. So till now you have decided what type of module you will use to complete this operation, but now you have to geometrically place them on the chip so that you can identify the total area of the chip you will be requiring. Or you can say that total bounding means the whole bounding box of the chip. Okay, so the other problem will be the routing. So one module to another module, the fluid need to be moved. So that's why routing will be another problem. So these two are the many means very well studied problem, that is placement problem and routing problem under this geometry level synthesis. So at the end, the final outcome will be this kind of chip layout. It may be regular shape, it may be irregular shape, it may be in case of continuous flow microfluidics, it may be the layout of the channels, and or it may be in the regular this PMD we have discussed. It may be the regular grid-like architecture of the CMFs, continuous flow microfluidics. Along with this, you have to have this actuation sequence. So what is this actuation sequence? Each and every timestamp, you need to know that which electrode to be on and which electrode to be off. So 0, 1 or 1, 0 sequence will be used for each timestamp. Now, if you have maybe 1000 timestamp, this information, this binary bit string, and this is loaded into the microcontroller and then connected to this electrode array, with the clock cycle of the processor of the microcontroller, you will be getting this this chip will be getting this actuation sequence from the microcontroller RAM or ROM. Then this will be acting like these operations. So finally, we are going to decide this actuation sequence and the layout, which are the final outcome for any synthesis or design problem. Okay, so I'm going to skip because I think I have almost covered 1 hour. So I have to skip some of the things to go to that quickly. So there are many issues. So I just shortly touching some of the things like this one. So this droplet routing, I think I told you about this, that routing is a problem in the geometric. Yes, in the last slide we were discussing that in geometry level synthesis, the droplets are moving from one location to another. So in that case, in order to avoid this unintended mixing, like you want to move one droplet and another droplet is also moving, but you don't want to mix them while they are moving. You want to mix them in the mixer only, but when they are moving from here to here and here to here, these two droplets should not mix. So in order to make this constraint, to restrict this operation, we need to add some constraints. So these are easy constraints. You can just easily verify that there should be at least two electrode gap, so that they cannot mix each other. So this is how different kind of another mechanism is also used, that is guard ring. So when there is a mixer, then around the mixer or around the module, some of the electrodes are omitted for routing the droplet. So these are the kinds of droplet routing problems. Another problem is cross contamination. When multiple fluids are being routed on the chip, then they should not, there should be less overlap, because if there is overlap, there is a chance of contamination. Contamination is just small amount of fluid which is left behind when a fluid droplet is moving. So here it is having like this. So if this is a scenario, and then in that case, people have worked on this washing of the fluid also, washing of the chip also on the fly. Because when the chip is working for a particular operation, particular protocol, they are also inserting the wash droplet to wash this kind of cells. So there are a lot of research have been done in this way, in this direction. And there is a simulator also people have developed in, you can see in the last decade only, last few years ago, four years ago, this simulator was developed by UCR, University of California, Riverside, USA. Philip Brisk is the professor and his student. They developed this simulator so that you can, anybody who are working on this domain or synthesizing this digital microfluidic biochip can, if they are developing some new algorithm, can validate here in this simulator. It is known as DMF SSS, static synthetic simulator. Okay, so there is another development which is very recent. I have taken, I think this is going on, means they are creating different versions. So the recent version is V4. So this is from Switzerland, Gaudi Lab. So they have developed this kind of kit which are controlled by microcontroller, Arduino kit, and is known as OpenDrop. And they basically use this kind of platform for testing or demonstrating the algorithm. If you have developed something and you want to control the electrodes using the microcontroller, you can load the program into the microcontroller using the USB cable into that Arduino kit, and then this program can run and make the mixing and all these things happening in the chip. So next, I think very shortly, I will talk about something. I will skip, sorry, I will have to skip some of the things which are not very essential. I think maybe this point, I want to discuss one problem here, which is design problem, which is called dilution or mixing problem. So it is basically the sample preparation. So when you are taking two different fluids and you are mixing them to reach a particular target concentration, how you can decide this graph. So this is a sequencing graph. So this is a problem where you know the target concentration to achieve for the sample, but in your architecture, if you are working with a chip where 1:1 mixing model is allowed, 1:1 mixing model is that one where basically you have two droplets of two different fluid, and then if you mix them, then you get the mixture of 2 unit volume, and then if you split, then you get 1 unit volume of the mixture separated. So this is called 1:1 mixing model. So it is basically the digital microfluidic biochip which is doing that. So if you have this kind of platform to implement this, to achieve this concentration of the sample, then how you will do this for any target concentration? What will be the algorithm to get this protocol? So this is one step ahead before that protocol. So I was talking about earlier that how from the protocol, how you can get the chip. Now I'm going to talk about how you can get the protocol or the graph from the given input target concentration. So you are given the target concentration, you have to achieve this graph. So that's the problem. So now if you are doing like this, then every time you are mixing, you are getting 2 unit volume, and one will be used for the next step and another will be wasted, because you are not going to use that, because next time you will mix with this and you will get this 75% of that sample, and then again you are mixing with the buffer, and then you are getting 37.5% of that sample. So like this, if you follow, then you have wasted some of the fluid, and you have taken maybe one mix split step here, and another mix split step here, and another mix split. So 3 mix split step. So after 3 mix split step, you got this target concentration here. Okay, and you have wasted 3 droplet. If you are not considering this, then it is basically 2 droplet you have wasted. So like this, there are algorithms people have developed, and these are very easy. So they have taken this concentration in binary form, just converted the decimal into binary, and then they have started mixing these two. So this is sample because this is 100%. This is same in numerator and denominator, and this is 0 by 1024. So this is 0%. So if they are taking this sample and this is buffer, they're mixing them and getting this 50%. This is 1 by 2. So 50% concentration. And then they start scanning these bits right to left. So this first one indicates this mixing, then is 0. 0 means you have to take the buffer. So if you take the buffer, then it will be half of this, because every time you are mixing, you are getting, what you are doing, you are taking the concentration 1 and concentration 2 equal amount. So C1 plus C2 and divided by 2, because those are equal volume. So divided by 2 is giving you 256 in the next step. So like this, if you follow the scanning of the bits, at the end you will get the same concentration with which you have started. So this is the innovation that they have done for developing this algorithm to get the directly acyclic graph, or the graph to, or the protocol, you can say. So there are other we did some work on that. I'm not going to discuss all this. Here you can see the paper of our paper in 2010 in TCAT transaction paper. And another one is simple to that previous one. So it talks about this ratio. You can see here 7 different reagents are taken, and there is a particular concentration which need to be achieved at the end. So it starts with the binary conversion. So here also you can imagine that there is a binary point, and then 0, 0, 0, 0, 5, 0, and then 1, 0. So this is 2. Okay, so 2 divided by 128, because this sum of these numbers is equal to 128. So if you do so, then this binary string is like this: point this, and then point this is 3. So like these, if you got the binary strings for all the 7 reagents, then you, sorry. Hello? Yeah, is there any problem? Okay. Okay, yeah. Okay, so if you are scanning these bits from right to left, then you put those labels in the bottom. Now, starting from the bottom label, so level 0, you just made up, then you will finally get the target tree like this. So these are the works. So those have been done during last 2 decades, maybe one decade or more. And then people have published a lot of papers on this, trying to develop some algorithms or design automation problems they are going to solve for sample preparation. Sample preparation is just mixing of multiple fluids, or making the concentration or making the dilution of a particular sample or one single fluid. So either in the dilution problem we talk about 2 fluids, or in the mixing problem we are talking about more than 2 fluids. So people have worked on this, and then their main objective is to design generate the graph, basically the graph that we are talking about, or the protocol we are talking about. Okay, so after doing all this, I think I will skip all this part. Now I will talk about some recent work that we did in the last 2 years ago. So it was published in Transaction. So it was talking about the reliability analysis of the mixture preparation using this digital microfluidic biochip. So reliability issue is coming here. As I told you earlier, that the split operation in ideal mixture is balance splitting. Like the concentration should be ideally half when this split is done. After mixing, this is C1, this is C2. So after split, this will be C1 by half, and means C1 plus C2 by half, and C1 plus C2 by half. So both will be equal. But what actually happens in the practical scenario is that they are getting there is some error incorporated. So it will be plus error in one droplet, in another droplet it will be minus error. So if it is minus error in this droplet, then it will be plus error in this one. So this is what is actually happening in the concentration. So how this concentration, due to this change in concentration in two droplets after splitting, can be analyzed, and then we can decide that which mixing algorithm, like the algorithm which is developing this kind of graph or the protocol, is better, or maybe means having less error which is occurring due to this unbalanced splitting. So the problem formulation was like this, that we have the target ratio and we have the target concentration factor, where these CXIs are the concentration factors of reagent XI. So we have an inner number of reagents, and we have some number of mixers to do on chip, on the digital microfluidic biochip. NM is the number, and each and every mixer can incorporate the error, and we have considered this error as a normal distribution having sigma I square. So depending on this mixer, this sigma I varies, but it is a normal distribution like behavior always for the mixers. So depending on these, that what is the output for this problem we want to get, that we want to determine that what is the error in the target concentration for each reagent. Like if you have inner number of reagents, then each and every one we have to determine in the mixture, target mixture. And then what is the reliable mixing tree and the corresponding mixer assignment. So which mixer to be used for which mixing operation. Like module binding we are talking about in the design automation issues, the same thing will be required here, that how these mixers will be used, which are having different varying your error incorporated by these mixers. So that was the output, and the objective was to first make a framework for Monte Carlo simulation that we did, so that we can understand about the erroneous behavior of the concentration, and then the analytical model. So we developed an analytical model to generalize this MCS, and then comparison of different mixing architecture. So our mixing architecture means that we can have different type of mixers on the digital microfluidic biochip. So we explore this different type of mixers also, that which mixer will be better, and find the final this mixer assignment having higher reliability. So which assignment, particular assignment, is there are 10 mixing operations and there are 10 mixers, and they are assigned to different mixing operations. Now which assignment will be better? So having the high reliability. So that we explored in this work, and there is some sequence of tasks we have performed here, as I discussed in the previous one, and we called it as a RAMT, that reliability analysis of mixing tree. And in this work, we basically proposed a brute force approach and then heuristic approach, and for this mixer assignment. And for the error model, we used normal Monte Carlo simulation for analyzing the behavior of error, and then analytical model we developed to quickly calculate the error, so that we can get the mixer assignment based on that error model. Okay, because Monte Carlo takes longer time to generate the results, so that's why analytical model was required. So by these by these slides, we basically, I'm skipping, but just giving the similar scenario that we have Monte Carlo simulation where the random samples are taken and large number of simulations are executed to identify the behavior of each and every error, okay, in the concentration or error by the distribution of the error of the mixer. Okay, so how they are basically incorporating the error in the concentration. Then the analytical model is basically used to find the error without random samples, such as such that this result is close to the Monte Carlo simulation. So looking at the multicolor simulation result, we backtrack and then try to find out that what could be the analytical model. So we explore these graphs, you can say that this directed acyclic graph or the mixing tree, which is directed graph, and then find out that how these errors are propagating from lower node to upper node. So this is the target node, the top one. The root node is the target concentration you are achieving, and this is the first node, second node, third node, fourth node. So these are operations, mixing operations. So we explore bottom-up approach and then find out that what could be the effect of this error in the mixers. So after that, we derive some analytical model for the error. After skipping some slides, I am showing this final one. So the details can be found in the paper, recent paper in transaction. So you can determine this error from this analytical model incorporated by a particular mixer in a particular node. So that was useful for our calculation for mixer assignment. So after exploring this, I think at the end, so this is the final slide that is showing that Monte Carlo simulation is incorporating this kind of error, modified concentration. How will be the modified concentration at this node, this third node, node 3, and then how will be the effect of, means how are the errors in this concentration for each and every reagent. So this is X3, X4, X5. So each and every reagent being mixed into this, and then the errors are basically considered. So this is how this error model has been considered. And this result is showing that how this analytical result is close to this Monte Carlo simulation. And then I think the reliable method. So which method? So there are existing methods, RMA, CODOS, and MM is min mix. We discussed already that bit scanning based method, and CODOS is the latest, is another method that was developed by other researchers, and RMA we developed. So we compared this distribution. We found out this distribution of error in this mixer assignment approaches. So different mixer assignment approaches has been compared here. So I think in the PMD that we discussed as advanced technology, we did some work, but time is very less. I will skip this one, and maybe I will go to another. I am giving a flavor of this. That here the problem is that in the mixing in the PMD, you can mix in a particular location, but after mixing, you cannot move one fluid to another. Means I want to mean that one cell to another cell, just this fluid cannot be moved, but you can have a flow from the inlet. There is an inlet, there is outlet, so you can have a flow. So this is how. So if these are the different constraints, then how a particular assay or particular protocol or mixing graph can be mapped into this chip. So that was the main problem here, design automation problem. So how to module bind this in such a way that the mixing can be performed without any transportation after mixing. Okay. So just only by fluid flow, it has to be controlled. So this we developed some algorithm and published in a conference called DATE, and some of the results have been shown here. I think another one I want to, this is interesting because it is also for PMD that I just discussed in the previous slide. So it is showing that this video is showing that there's something is being mixed here. Okay, you can see that how these fluids are loaded into the chip. So one by one, cells are loaded, and every time you need to send a flow from this inlet and send this flow through this outlet, and you can fill the desired number of cells and particular cells which one you want to fill. So this is how this PMD chip works. You can see the demonstration, a real video. This is basically the real video they have shared in the paper. So in this case, that how many times this loading fluid is to be executed. in order to load multiple different type of fluids into different cells. So that was the problem here in our case. And we worked on this starting from a bioassay. So some real life bioassay we talked about, we discussed, and this is a protein assay, which is well known, means very popular assay in biochemical laboratory. So how this can be mapped on the PMD chip, and how this loading, fluid loading is automatically can be designed or maybe minimized, basically number of loading cycles. So that was the problem. So we developed some algorithm for doing that. So this is one of them, that is determining from the last flow, DFL. This is the one approach that we developed, and the paper we published in this year, last year also. Last year the conference version, and then we extended that work with another problem and published in this year in Integration Journal. So like this, I think the extended problem was on this LAFCA, that is loading our fluid to cell assignment. That is another problem, that how to assign the fluid into the cells. So if you can change the assignment of the fluid into the cell and then you load, then it will be, it may be better results. So if you change the assignment of the fluid into the cell, how to do that? So depending on the loading overload. So there is a Hamiltonian path-based approach that we have talked about in this paper in integration. So I think that's our recent work, and I want to skip the details, much more details, but this is another recent work that we did on MIDA. MIDA is, we discussed the advanced digital microfluidic biochip array, that is microelectrode dot array based microfluidic biochip. In that, we talked about one algorithm for dilution, and that talks about different kinds of modules, how they can be automated. So still a lot of things. Maybe I do not want to discuss this. There are some simulation has been shown that the existing work, how it did when this tree is being mapped into the chip, then how is the scheduling working. The previous basically the previous work, that CLOSPER-D and the WSPM, but we proposed this one in recent paper in 2021, and we have shown that this is how the scheduling can be faster by using this new algorithm, and it can run faster, and also it can consume less fluid also. You can see the height of the tree is also less, and also the consumption of the fluid is also less. So this is how we applied some factorization based approach. So factorization of the number, so number partitioning based approach we applied, and then we have shown this simulation results. So I'm not because maybe it will not be useful if I go into detail of this, rather than I skip this and go to the last part of the talk, so that I can finish maybe soon. It is already 1:30. Okay. So these are the different algorithms we have. You can see in the literature starting from 2006. Maybe these blue colors are the work we did, but the black ones are the other people have done. So this is a well studied research field, and many people have worked on this. Many different papers you can find in the literature. So this is a list of them. Some of them maybe I have missed some of them. Mostly the major papers are already listed here. So this is on dilution algorithms, that how they develop the protocol for the dilution, and and this is the mixing algorithms, how they develop different things. So now cyber physical integration of digital microfluidic biochip, as we came to know already, that there is a computer or maybe the microcontroller which is controlling these electrodes and also sensing the data by camera, or you can say that photodiode and LED bits arrangement. So it is basically a cyber physical integration which is involved here with this chip. So when you are involving computer and all this data communication from this chip, so there will be requirement of its other issues like security issue, so that people cannot attack this chip and tamper the result and show that you are already infected, but although you are not infected, or maybe if you are infected with that disease, you are already having the thing, you are getting negative result. So it should not be like that, because it can create a huge problem in the society. So that's why security is a very important issue in this kind of chip. So cyber-physical integration of digital microfluidic biochip for error recovery. One work you can find here, that maybe sometimes some errors are already is basically coming from the device, and how due to this error, how the error can be recovered. From this error, this means the results can be reliable without even there is an error. So this kind of work has been published recently in maybe last decade in 2013 in Transaction. And you can find other work. Okay, this is another work which talks about different type of bioassay. They start they basically one bioassay they talk about, and they show that how these firmware, basically the data collection and the analysis, this part. So biochemical device, biochip device and the sensors, this is one part, and there is a software synthesis, which is a computer part, so cyber physical system, and there is a data collection and analysis part, which is firmware. So the signals are coming from the sensors from this biochip, and the decisions about the protocol flow is decided by this firmware. So depending on the output of the signals, it decides what will be the next step. So so that this adaptive resource allocation scheme is executed, and the new resource allocation is done on the, or the module binding is done on the chip, and then the corresponding control signal is generated by the software, and it sends the control signal to the chip to again operate according to that decided new actuation sequence. So this is how this currently means this kind of chips are being controlled by a cyber physical setup. Okay, so I think security issues in the microfluidic biochip, if we talk about, so in hardware security or the cryptography, we know that the sample encryption and decryption process. So there are basically plain text we have, and some algorithm we have, and then a ciphertext we generate. And in case of decryption, we have the ciphertext, we have the key, and we have this algorithm to get the plain text. So now we think of this problem that the actuation sequence. So where the situation happens, so you have the actuation sequence designed, means basically developed along with the chip layout. Now this actuation sequence is basically binary stream, so binary file. So if you're giving this information, that chip layout and the actuation sequence both to some third-party vendor. So the designer has designed this, all these things, and then foundry in which that chip is fabricated, and another assembly industry, which is basically getting the software, this control sequence, and loading into the microcontroller. Now these will be assembled or integrated. So now both of them have the information about the this bioassay. So it is important to encrypt somehow this if you can encrypt this actuation sequence and also the layout information in such a way that this during this communication with the vendor and the third party vendors, no other intruder can see that and then get the information. So this is to secure the communication between the designers and the foundry and the integrator or the system designers. Okay, so there are a lot of different security threats possible in the biochips. One is this man-in-middle attack. The attackers secretly rely on possibly alter the communication among the parties. So there is a communication. So man-in-the-middle attack may happen during the communication among the designer and this foundry and the tester. So there are different partners involved in this whole process, as it is a cyber physical system and designed by the computer. And this is also possible that that hardware Trojan attack. Okay, so that some malicious alteration of the chip is already made, and then the attackers can insert this hardware Trojan by modifying the chip biochip design during the manufacturing time. So when the foundry is going to do that, it is basically making a faulty chip. Not faulty, maybe it is working, but it is having this hardware Trojan inside this, which can alter the result of the chip. So this is another kind of, and the piracy attack, that is attackers easily duplicate the IP of the biochip during their communication. So it just take the IP and then it create a pirated version of the chip. So this is another kind of attack. And the bit flipping or sequence or the complete substitution attacks. This is another kind of attack which is possible, that is based on the replacement principle. Okay, so it is in this attack, the single bit or the n bits or the whole actuation sequence is modified. Okay, so or deleted or inserted, whatever may be possible, the intruder can do that with an alternate sequence. So if it is being done, then the actuation sequence is got changed, and then your chip will do some malfunction, and it may give highly possible that it will give the wrong result. And the other one is this denial of service attacks for the digital microfluidic biochip, where this cross contamination is basically one issue, which is due to means cross contamination. I discussed earlier that once one fluid moves through the electrodes and another fluid is also flowing through the same path, following the same path. Maybe the previous fluid or droplet has failed some residue, and in that case you will find the cross contamination. So if this is cross contamination, this may also raise to this denial of service attack, because it can change the operation of the assay. Then alteration of the sample or assay specification. So specification is already changed. So assay specification means the graph. So somebody has altered already the graph. So if the designer is taking the program of that graph or the instruction sequence, it is already altered, then the whole thing will change. That chip will not properly work, and all maybe giving the wrong results. So these are the different attacks, denial of service attacks. And other two are electrodes actuation low level sequences. This is another one, and prolong the droplet route. So droplet route can be prolonged. So it is rotating for longer time, although it can reach from this to this location, but here you can see from this to this location, but it is prolonged to reach by this way. So if the actuation sequence is changed in such a way that this is called a denial of service attack for this digital microfluidic biochip. Similarly, the hardware trojans are on the digital microfluidic biochip I discussed already. So what are the solutions people have talked about till now is that people first the authentication technique to prevent the IP piracy of the digital microfluidics is based on the physically unclonable function. So PUF have been used for the authentication purpose. Okay, and the other techniques are like bioassay locking by fluidic multiplexer. So fluidic multiplexer is a new technology. That is not technology, means you can think of another module. So it can multiplex multiple fluids. So fluidic multiplexer they designed, and they have locked basically the bioassay. So without that multiplexer is selected, that select line is activated, the correct result will not come. So it is basically controlled by this fluidic multiplexer. And the fluid and another technique is that people have worked on and published is that bioassay locking by randomly inserting dummy mix split activities. So they basically in the assay or the protocol graph, the randomly some dummy mix split activities have been inserted. Although those are looking as a mix split assay, the intruder will think that this may be the actual operation, but it is dummy. So the bioprotocol will not change if the intruder affect these dummy nodes. Okay, so that's how they basically handle this. Is another technique. And the digital rights management scheme using locked final state machine. So this is another technique, and I think that there are many such things, and the survey is already there, so you can find some good number of survey. Basically, there is a survey paper also, available in the literature, which list all these kind of maybe all these kind of security issues, how they have incorporated in the microfluidic biochip. So in our work, we in one paper we published this year, we talked about the security model for protecting the intellectual property of state-of-the-art digital microfluidic biochip. We here considered about all kind of microfluidic biochip, and discussed about that how these communication. So basically, IP designer who is basically designing the chip and the authorized parties. There are many authorized parties possible, different ways. So they are communicating, and in this communication, they are basically sending the actuation blocks, actuation sequence. So we proposed a technique that how this actuation sequence can be basically secured by using some tweak calculation and XOR with this tweak, and then encryption with AES. So we use AES here again, and then storage device in the communication channel, or communication channel goes through that, and decrypted in the other end by using this protocol. So this is this technique we called is as the securing the actuation sequence using XOR based tweak. So that is known as SAST, and this talks about the security mechanism for for this kind of chip. I think I will not go to the detail of this. You can find the detail in the chip in the paper. This GISA paper this year in Elsevier journal. And then I think the last that I want to talk is about the layout. So the microfluidic biochip layout is a geometric information. So it's talk about basically it is giving the details about the chip geometry. So which is basically written as a GDS2 file. So GDS2 file is common in VLSI chip design also. So the chip layout is basically written in a file which is called GDS2 file. So we also talked about this kind of chip layout, how this GDS file block can be secured. So my student, PhD student, published this paper in this year in Transaction of Computational Biology and Bioinformatics. So in that paper, he talked about this chip layout encryption. So basically GDS2 file encryption. So you can see here that bioprotocol coder and the CAD tool vendor both are working with this IP designer, and they are communicating this information. That one is giving the tool, software tool, for designing the chip layout from the sequencing graph, and they are encrypting this IP. This is intellectual property, basically, the chip layout and the actuation sequence. So they are using these parameters, this K1, F, and C, and then sending basically to the foundry in the encrypted format. So the foundry is then design the custom chip, or it may be the application specific chip, you can say, send it to the biochip tester, and this tester is taking this chip to decide whether it is correct or not. And in order to run the bioprotocol, this biochip tester will require the actuation sequence, and that is also encrypted form. It is sent to the biochip tester from the IP designer. And the end user, after getting the good biochip, tested okay kind of biochips, they can use that chip using the encrypted actuation sequence. So this kind of work is basically was not there. So that's why we means my student wanted to focus on this, the PhD student, and he did his PhD on this topic and published these two papers on security of biochip. So this work was known as this LETCE, so layout encryption using XOR based extended tweet block chaining mode and cipher stealing, and including this error control mechanism. So it has some error control mechanism also. Not going to detail, and these are the different protocol name on which the simulation have been done for different calculation of different file size, layout file size, and the biochip assay. Okay, so I think that's the discussion on this biochip and the security issues of the biochip that we explored, and a little bit of the literature survey. I wanted to, I just mentioned in the beginning that I will show you some recent development. This is not very recent, but maybe more recent video you will find in the internet. So this one is showing that how this microfluidic biochip, there is a small microfluidic biochip you will find here, okay, here. And this is being controlled by the mobile phone. There is a mobile app, and it is being some kind of protocol is actuation sequence is loaded here, and it is sending the control through the Bluetooth connection, and the fluid actuation is being happened on the chip. So you can see the open valve, close valve, like this kind of operations for the different time in second, protocol start, all these things are there. Okay, so if we summarize in total, that we have to focus on the cyber physical system, and to target solving the problems, we need to understand the physical system. That's why I discussed the many things about the architecture of the chip or the technology, the emerging technology we talk about, and the design algorithms we need to know for solving the automation problem and automation things. And we have seen that how computer architecture, operating system, compiler knowledge or programming knowledge are important here. And there are lots of scope to apply machine learning also in this domain, because the sensors are collecting the data, and based on this data, the application can be developed, which will be useful for analyze and deep learning and computer vision also, because the camera is involved there for taking the image of the chip top view. And the computer vision based work has also been done. People have worked on this also, and they have used this computer vision based algorithms for the automated diagnostics. Okay, so and then security, that cryptography and hardware security related issues are also important in the design automation problems. So it's an interdisciplinary topic. So computer science, electronics, mechanical, chemical, and biomedical engineering, microfluidics, sensor technology, and medical science. All these are involved in this topic, but still a lot of research is required. People are working on this, and due to this corona and COVID, people have also done some of the recent research on this RT-PCR kit, which are readily available now, which are based on microfluidics. So I think in future, maybe some of the students may work on like this for developing algorithms and focus on these security issues for this kind of chips. So that's all from my side. Yeah, thank you for your attention. I have taken long time, so I think almost 2 hours. Sorry. Yeah, that's all from my side. Any question?
So thank you so much, sir, for such a wonderful session. So now if anyone having a doubt, so she or he can put it onto the chat box or unmute yourself.
Sir, I was having one. You said about the DAG input file. We were having nodes in it. So for what purpose the nodes are for, sir?
Oh, okay. So the nodes are representing the operations, and in the graph, you need to basically in the sequence of steps, you are written the operations, and in the graph you want to visualize that operations as a node. So that's why this node information is important, and the edges are representing the dependency, the precedence, which node to be executed. So nodes are basically the operations. It's as simple as this. Is it clear? Or
yeah, sir. Yes, it is clear. So one more, like you said about the droplets inside the electrodes. So of which fluid it is of?
I couldn't understand. Can you please repeat?
So there were droplets inside the electrodes, between the two electrodes.
Yeah. Between two electrodes, yes.
Yes, sir.
Yes.
Yes, sir. So, of which material the droplets were of?
Oh,
They were
okay.
of microfluid. Yeah.
Yeah, droplets are basically this human physiological fluid. So this, it depends on the fluid with which you are working. So it depends on the protocol, bioprotocol. So if you are talking about this, just very recent example is this RT-PCR test. So you are basically focusing on this saliva, or maybe you can say this nasal swab. Okay, so this is the fluid. So droplet is in picoliter volume or femtoliter volume, which is diluted maybe, so that you can create a small droplet having this fluid, saliva or this. So, and also the reagent that is being used to make this PCR test. So those are also fluid. So droplets are a mixture of these, and this droplet is moving to that detection unit, and then you are getting this analytics or analysis data, analyzed data. Maybe that two electrode I told about. So the droplet in between these two is basically the after your the operations are done, mixing and splitting.
Yeah, you got it, sir. Thank you, sir. It was an excellent session, sir.
Yeah, okay. Thank you.
So now the feedback link will be given into the chat box. So everyone fill the feedback and give your valuable feedback.